The professor said, introduced in the yesterday's lecture, we have some time complexity analysis for different types of algorithms. For example, like a sorting algorithm, here we're showing we have some so-called comparison-based sorting algorithms. And specifically in analysis algorithm, if you guys have the textbook, CLRS, did you guys ever heard of this textbook? Introduction to Algorithms is a very classic textbooks. There's what is it? Yeah, there's I don't remember. It's a lemma or something. Well, it's just said all comparison-based sorting algorithms have a complexity lower bound of n log n. That means it cannot be faster than n log n. So here's a table. Yeah. So here's a table of some types of the comparison-based sorting algorithm. So the first one is the bubble sort. Next one is selection sort, insertion sort, quick sort, merge sort, heap sort. Very classic three is the quick sort, merge sort, and heap sort. These three algorithms will be covered in the CLRS. So you can see here the time complexity or the time required to run in this algorithm is omega n log n. So that's why this three is the fastest algorithm for comparison-based sorting. So I probably just show you guys the bubble sort, quick sort, and merge sort, and heap sort. So this is algorithm. This is a script I found it on the internet, and I calculate the initial time step, and I assign to T1, and the second one I assign to T2. So at the end, I print out the delta time between the T2 and T1, and I have a time unit of milliseconds. So let's see. So the sorted array of these given numbers here is 11, 12, 22, 25, 34, 64, and 90. And the running time of this algorithm is 0.08 milliseconds. An issue here is we probably not gonna have such conclusion because the n here is almost like a infinite numbers. But here we have what's the n we have here is 1, 2, 3, 4, 5, 6, 7. It's only 7 numbers. If we have a let's say 1 million numbers to be sorted, we can draw a picture or a curve of this. Let's say quick sort. Big O curve. Yeah, we can draw such a picture because the elements here is large enough. If we have very small numbers of our elements, the result might not be equal to the conclusion we have here. So let's see another sorting algorithm. Let's see merge sort. This is C++. This is Python. Yeah. Similarly, we ran a time analysis. So you can see the merge sort here. We have 0.03 millisecond, which is faster than the bubble sort. They have a 0.086, right? So when you're programming something, the current stage, we probably just finished the task, right? Required by the home assignment. But in real world engineering problems, what we need to show not just the task, but also we need to run some efficiency, right? For example, like if you search something on Twitter or Facebook or Google, the longer time you got a response, the worse user experience you're gonna have, right? So that's why we need a faster algorithm to running this let's say sort, search, some basic operation. Well, for those students just shown here, I think this is for Lab 7. There's some sorting algorithm and algorithm analysis. So I introduced a little bit earlier here because Professor mentioned this yesterday. So next one, let's see the quick sort. Let's also measure the times. Measure the times here. I don't know why. It seems slower, 0.15. Yeah, it's slower than the previous two. As I said, because our sample is quite small, so if you wanted to have this kind of curve, what you need to do is you need to do multiple experiments for example, like 10 at least. Maybe you have 10 samples, 100 samples, 1,000 samples, and 10,000 samples, sort of things like that. And then you measure the time here, and then for each algorithm, you can draw a curves here. If you're interested, you can do this experiment by your own. So next one, let's see the heap sort. The heap sort, I'm not sure we're gonna run it because you need to use a binary tree as another data type. Is not an array. It's a specific complete binary tree. So here is a binary tree. I don't know whether we can run this. Heapify, yeah. So the Python have a internal function called Heapify. You're probably going to use it in the following assignment. That means change this data type into a heap. So I guess it's probably going to be easy to run this. This is not Python, right? Yeah, here's the Python. The red characters here is because the indentation is wrong, because normally we have 4 space here, and since I copied from here, it's just not correct, so I changed the indentation to make the program run correctly, I hope. So this is the heap sort. Let's measure the time here. So 0.119 milliseconds. It's also slower than the previous first two. But as I said, you need to do multiple experiments to draw such a curve. So this one is ideally faster than the others. So the current elements we have is so small. So if we wanted to have such a conclusion, we need to expand our numbers into, let's say, infinite elements of this input. Okay, so this is today's sessions. Where's the recording?